Hello everyone, I'm Jaehoon Kim from Hanyang University. Today I'm delighted to share our paper, Labor Hard Negative Sampling Strategies with Momentum Contrast Running for Implicit Hate Speech Detection. This work is from our team, Hanyang Human Centered Computing Lab. First, I will briefly talk about the contrast running, which is the core concept of our study. We leverage the supervised contrast running to improve sentence representations by using labeled data to distinguish between similar and dissimilar text samples. The domain of this study is hate speech, so in this field, recent work has started to highlight implicit hate speech than explicit hate speech, so the two concepts have the following characteristics. Explicit hate speech uses direct profanity or hateful messages. Implicit hate speech uses metaphorical and implied messages to indirectly express hatred. In particular, implicit hate speech is harder to detect than explicit hate speech, and this is true for both humans and language models. As you see, the implicit hate sentence on the figure has an implied message targeting Mexicans. This is hard to predict as hate without the background. So, how can we teach the model to detect it? Let's think about it from the model's perspective. In the figure, the anchor is a hate speech targeting black folks. And the age negative sample is easy to distinguish from the anchor because it has a completely different context than the anchor. On the other hand, the hard negative is not easy to distinguish from the anchor because it has a similar context to the anchor. According to the previous studies, if the negative sample trained along with the anchor is similar to the anchor, the model can be trained to better distinguish relatively indistinguishable data. So, to train the model to catch the subtle differences between implicit hate speech and non-hate speech, it's important to train on hard negative samples. So, how can we consider these points to the training process? This is our key idea. Previous work has used contrast running, which encourages contrast between data in randomly sampled mini-batches. The random sampling method randomly selects negative samples in the training dataset except considering hard negatives. On the other hand, ours only selects samples that are similar to the anchor but in a different class in the training dataset. I'd like to detail our method in the next slide. This is our overview figure. The first is Moku. Instead of considering all samples in the queue as negative samples, we consider samples in the momentum queue as candidates for hard negative extraction. The momentum contrast was proposed in Moku to overcome GPU memory limitations and allow large amounts of data to be used as negative samples in the contrastive running. And next is the similarity weight. To consider the similarity between the anchor and all negative samples in the momentum queue, we employ the cosine similarity. By weighting the prediction probability from the model to the cosine similarity, we can focus on negative samples that confuse the model. The final is hard negative sampling. We sample hard negatives by sorting all candidates based on their rated cosine similarity. The number of hard negative samples selected depends on the parameter k, which adjusts the number of hard negatives to assign to the anchor. Using this framework, we can train the model with hard negative samples. We use the two losses. First, cross-entropy loss adjusts the model to better predict the actual labels, and contrast running loss adjusts the model to pull the anchor and positive samples closer and push the anchor and negative samples. We use the combined final loss, and this loss was proposed by supervised contrast running for pre-trained language model fine-tuning. We used four datasets, each designed to evaluate the model's ability to detect implicit speech in various contexts. So now, let's explore our experiment's results. We used two training datasets and four evaluation datasets, and we used two pre-trained language models. And in the table, the checked externality items mean that the positive samples suggested by ImpCon were used. By ImpCon, the authors proposed to use the implication of hate speech as a positive sample in contrastive learning. So the next is our operation study. In our operation study, we explored the individual contributions of components, the momentum contrast, and the hard negative sampling and the cumulative weight. As you see, our methods contribute to overall performance on step by step. Increasing the number of simple negative samples with MoCo causes a performance drop. But our method, the hard negative sampling and the cumulative weight strategies with MoCo lead to performance gains. This is our visualization result. We use multi-target topic data and hate, non-hate labeled data. Our spawns clear clusters, even both multiple target topics and hate, non-hate labels. Our two visualizations show that ours leads the model to form a more high-quality representations. Finally, we investigated the effects of hyperparameters. In the figure, the x-axis denotes the hard negative sample size and y-axis denotes the momentum Q size. In this part, we found the following two findings. The performance of our framework is not dependent on any particular range of parameters, and simply increasing the size of the momentum Q and the number of hard negative samples does not guarantee linear performance improvement. So, we found our framework has robustness on the side of hyperparameter sensitivity. In conclusion, we provide the following insights. The development of a generalized implicit hate speech model remains challenging. To improve implicit hate speech detection performance, it is important to capture subtle differences in expression. We need to better utilize the context of implicit hate messages to improve implicit hate speech detection. And in our future work, we should explore a better semantic similarity metric than the cosine similarity, and exploring implicit hate speech detection methods using LLMs is one of our future work. Thank you for listening to this presentation and for your interest in our work. Thank you.